Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into reinforcement learning via self-play. It's a fascinating area, so let's get started. What are your initial thoughts on the topic?
Self-play, especially when combined with deep learning, has produced some pretty impressive results, right? Think about AlphaGo. That was a watershed moment. It learned to play Go at a superhuman level purely by playing against itself. That's a huge leap.
Yes, AlphaGo was impressive, but I still have reservations about attributing real intelligence to something that's essentially mastering a single, albeit complex game. It's optimization, not understanding. It doesn't understand the why behind the moves.
I agree with Sarah to some extent. AlphaGo is great at Go, but it can't, fold laundry. The problem is the representation. Go has a perfectly defined board and rules. The real world, not so much. That's where spatiotemporal reasoning comes in. How does it take into account that the floor might be uneven, or that the laundry basket might be full?
That's a good point, Donald. The difference between a well-defined game environment and the messy, continuous nature of the real world is significant. But Otto, you were talking about the success of deep learning and self-play. Can you elaborate on that?
Sure. The beauty of deep learning in this context is that it can learn incredibly complex patterns from raw data. It doesn't need to be explicitly programmed with heuristics or strategies. It discovers them on its own through millions of games. You have a neural network, you let it play against itself, and it gradually gets better and better. The reward function signals progress, and backpropagation tweaks the network's weights to improve performance. It's a powerful, albeit data-hungry, approach. This is one reason I think we are on the path to AGI, more data.
But isn't that data-hungry aspect the problem? We, as humans, don't need to play millions of games to learn a new game. We grasp the rules and maybe play a few practice rounds, and then we're competitive. Deep learning requires massive amounts of data and compute. That feels brute force, not elegant. There has to be a better, more efficient way, one that can combine learning with existing knowledge.
Sarah, I think that's a crucial point. The efficiency of human learning is astonishing. It suggests there are unexplored principles at play that we could incorporate into our AI algorithms. Perhaps the way humans can generalize their learning to novel situations can offer insights.
Yeah, and the thing is, the reward function is often artificially defined, right? Like in a video game, the reward is points. But in the real world, rewards are much more nuanced and distributed in space and time. An autonomous car, for example, has to deal with a continuous stream of sensory input and make decisions based on a complex understanding of its surroundings. It's not just about maximizing points. It's about avoiding accidents, navigating traffic, and reaching its destination efficiently. The car is translating between different coordinate systems, GPS, physical space, speed, etc.
That's true, Donald. Defining the reward function is critical. A poorly defined reward function can lead to unintended consequences, where the agent learns to exploit loopholes or optimize for narrow metrics rather than the intended goal. But I think, with enough carefully curated data and iterative refinement of the reward function, we can overcome these challenges. The emergent behaviors we're seeing are exciting. They suggest that deep learning is capable of more than we initially thought.
But the emergent behaviors are often still quite limited. They might be impressive within the context of the specific game or simulation, but they don't generalize well to other domains. I think we need to move beyond end-to-end deep learning and incorporate symbolic reasoning. We need to give the AI a way to represent and manipulate knowledge in a more explicit and structured way, like a neuro-symbolic approach.
So, you're suggesting combining the pattern recognition capabilities of neural networks with the reasoning power of symbolic AI. How might that work in practice, Sarah?
Well, imagine an autonomous car again. Instead of just feeding it raw sensor data and letting it learn to drive through trial and error, we could give it a symbolic representation of the road rules, traffic signs, and other relevant knowledge. The neural network could then learn to map sensory input to these symbolic representations. And the symbolic reasoning engine could use this information to make decisions about how to drive. This would allow the car to reason about its actions and generalize its learning to new situations more effectively. For instance, if there is a detour, the car should know to go left.
That sounds promising in theory, but the challenge is how to seamlessly integrate these two approaches. Symbolic AI can be brittle and struggle with uncertainty, while deep learning can be opaque and difficult to interpret. Combining them effectively is a non-trivial task. Also, the scalability of a symbolic component can be problematic when trying to apply it to increasingly complex situations.
I think a key piece of the puzzle is how to represent space and time. How do you translate the symbolic rules of the road into the car's internal representation of its environment? How does it understand that a stop sign applies at a specific location and time? How does it know where it is relative to that stop sign and how fast it's approaching? It needs to translate between its GPS coordinates, its visual perception of the sign, and its internal model of the road network. If you can't translate, then it will run the stop sign.
Donald, that idea of translation is very interesting. It resonates with the brain's ability to integrate sensory information with existing knowledge in real time. How can we build that seamless interaction into our AI systems?
I think we're already seeing progress in that direction with things like attention mechanisms and transformers. They allow the model to focus on the most relevant parts of the input when making decisions. It's a form of dynamic feature selection, where the model learns to weight different aspects of the input based on their importance. The focus on efficiency and LLM reasoning could drastically reduce compute costs.
But attention mechanisms are still operating within a purely data-driven framework. They're learning to attend to certain patterns, but they don't necessarily understand the meaning of those patterns. It's correlation, not causation. The LLM has no idea about the meaning behind those words. It is just an association. It needs to be grounded in something more fundamental, like a symbolic representation of the world.
Exactly. And that symbolic representation needs to be spatiotemporal. It needs to encode not just the objects in the world, but also their relationships in space and time. The car needs to know not just that there's a pedestrian, but also where that pedestrian is, how fast they're moving, and whether they're about to step into the road. I suspect the core algorithm needs to be able to translate between different coordinate representations. The translation algorithm becomes the core AGI algorithm.
So, you're suggesting that the key to AGI is a kind of universal translator that can map between different representations of space and time.
Yeah, something like that. A system that can take input from different sensors, translate it into a common representation, and then use that representation to reason about the world and make decisions. Current deep learning is brute force, but it may be possible to use it to perform translations.
That's a very compelling vision, Donald. It suggests that we need to focus on developing algorithms that can learn to represent and manipulate space and time in a more flexible and powerful way, perhaps by studying how the brain does it.
I still think that deep learning offers the most promising path forward. The brain may be an existence proof that intelligence is possible, but it doesn't necessarily mean that we need to mimic it exactly. We can learn from the brain, but we don't need to be constrained by it. I think we can achieve AGI through a combination of deep learning, reinforcement learning, and self-play, driven by massive amounts of data and compute. The current focus on increasing massive data sets to achieve AGI is a direct manifestation of the fundamental principle that data-driven methods yield improved results with more data.
But the brain's efficiency is something we can't ignore. Throwing massive amounts of data at the problem isn't working. The models lack common sense. They hallucinate. They can't adapt to new situations very well. I think neuro-symbolic AI is the way to go. We need to combine the strengths of both approaches, the pattern recognition capabilities of neural networks and the reasoning power of symbolic AI.
And that combination needs to be grounded in a spatiotemporal framework. How do you represent the symbolic knowledge in a way that can be integrated with the sensory input? How do you translate between the symbolic representation and the neural network representation? How do you represent the uncertainty in a symbolic system? Without a solid translation method, it will never work.
I agree that uncertainty is a challenge, but I think we're making progress on that front as well. Techniques like Bayesian neural networks and variational inference allow us to quantify the uncertainty in our predictions. We can use this information to make more robust decisions and to avoid overconfidence. I've been delving into the theoretical underpinnings of reinforcement learning, specifically how the reward function is defined and how it influences the agent's behavior. There's a significant potential for bias creeping into the design of these reward functions, which may limit the scope of learned behaviors.
But even with uncertainty quantification, the models are still fundamentally black boxes. We don't really understand why they're making the decisions they're making. That's a major problem, especially when we're talking about deploying these systems in safety-critical applications. How would you explain the decision made by an AI system to someone in simple terms?
That's where the spatiotemporal framework comes in again. If we can represent the model's reasoning process in terms of transformations between different coordinate systems, then we can at least have some insight into what it's doing. We can say, the model transformed the visual input into a set of spatial coordinates. Then it used those coordinates to infer the pedestrian's trajectory. Then it used that trajectory to predict the probability of a collision. I'm intrigued by the possibility of formalizing the rules governing coordinate transformations. If such a formal system could be developed, it might allow for a more structured and predictable path to intelligence, instead of the seemingly random optimization process of current deep learning approaches.
So it sounds like we all agree there are limitations to the current deep learning approach, even when combined with self-play. The question is, what are the next steps? How can we move beyond brute force learning and build more intelligent, adaptable, and trustworthy AI systems?
I think we need to continue exploring the power of deep learning, but with a greater focus on interpretability and robustness. We need to develop techniques for understanding why these models are making the decisions they're making, and for ensuring that they're not just exploiting spurious correlations in the data. Also, how can we better measure the efficacy of different deep learning architectures at capturing nuanced reasoning patterns? Are there objective metrics, beyond simple accuracy, that better reflect the depth of understanding achieved by an LLM?
I think we need to invest more in neuro-symbolic AI. We need to develop frameworks that allow us to seamlessly integrate neural networks with symbolic reasoning engines. This would allow us to build systems that can learn from data, reason about the world, and explain their decisions in a clear and understandable way. Also to investigate hybrid neural symbolic systems and find examples of algorithms that combine the best of both approaches in a way that avoids the limitations of either one in isolation.
I think we need to focus on developing a more fundamental understanding of spatiotemporal reasoning. We need to develop algorithms that can represent and manipulate space and time in a more flexible and powerful way. This might involve exploring new mathematical frameworks or developing new hardware architectures. If AGI is truly achievable, wouldn't an effective core algorithm require a sophisticated language of space and time to represent and manipulate complex concepts? How might one translate between visual, auditory, and even abstract representations of spatiotemporal information?
From my perspective, I think we need to look to the brain for inspiration. How does the brain integrate sensory information with existing knowledge? How does it represent space and time? How does it learn so efficiently? By studying the brain, we can gain valuable insights into the design of more intelligent AI systems. How can we leverage insights from neuroplasticity to create more adaptable and resilient LLMs? Current models seem brittle. Can dynamic adjustments in neural pathways, mirroring the brain's learning process, lead to greater robustness and generalization in complex reasoning tasks?
That's a great point, Jesus. It's all about finding the right balance between neuroscience, AI, and computational power. I think we're on the cusp of some major breakthroughs. The sheer volume of data needed to train deep learning models, especially for complex reasoning tasks, suggests that the path to AGI is likely to involve a synergistic approach of improved data quality, algorithmic refinement, and an increased understanding of the underlying cognitive processes themselves. I want to explore how we can leverage the power of large data sets in a way that maximizes efficiency and ensures generalization beyond the training data.
I agree. It's a multifaceted challenge, and we need to approach it from multiple angles. But I remain convinced that we need to move beyond the current paradigm of end-to-end deep learning. It's not enough to just throw more data at the problem. We need to develop algorithms that can truly understand the world. The idea that deep learning alone will lead to AGI feels increasingly naive. Is it not clear that human intelligence relies on a combination of symbolic manipulation and learned associations, not just raw statistical correlations?
And that understanding needs to be grounded in a spatiotemporal framework. We need to develop algorithms that can represent and manipulate space and time in a way that's both flexible and powerful. I think that's the key to unlocking true AGI. The current focus on brute force deep learning feels like trying to assemble a complex machine by randomly throwing parts together. I suspect a more fundamental understanding of coordinate transformations between different spatiotemporal representations is crucial to a more elegant, potentially more efficient, approach to building intelligence.
This has been a fascinating discussion. It's clear that reinforcement learning via self-play is a powerful tool, but it's just one piece of the puzzle. Building truly intelligent machines will require a deeper understanding of neuroscience, symbolic reasoning, and spatiotemporal reasoning. Thanks for joining us today on Cognitive Spirals. Until next time.